All right, so I'm Brian, and for my midterm seminar presentation, I'm going to be talking about deep learning for recommendation systems. So, first things first, why recommendation systems? Well, it's useful in a variety of contexts, but kind of the most compelling and the most widely used application of recommendation systems is for any content focused platforms. So, things like YouTube or Spotify or TikTok. Um, Basically, for your users, you want to recommend them different kind of content that they might like, therefore keeping them on the platform, and that generates money for the companies that these platforms are developed by. And previous approaches would use things like filtering or collaborative filtering, which is really accurate and works really well. But one of the problems is that there's a lot of engineering overhead involved with those approaches. And with deep learning, you can hopefully get to a place where the accuracy is just as good as collaborative filtering methods, for example, or even better than that. For this presentation, I'm going to be going over 4 different approaches to recommendation systems with deep learning. So the first paper we're going to go over is Widen Deep Learning for Recommender Systems, which was an attempt by Google. It was written in 2016, and kind of their main contribution was proposing this model that could jointly train between a wide component and a deep component, which we'll go into the details of later on. The second paper is on a model called Deep FM, and kind of the key contribution was giving an end-to-end model that doesn't need to have different inputs for the wide and deep components, which again, we'll go over the details later on. And this paper was written by some of the engineers at Huawei. The third paper we're going to be going over is on deep and cross networks, which basically allow for higher order feature interactions in terms of the learning process. And this was written by some of the folks at Google. And the last paper that we're going to be going over is a really new approach by Facebook, which is currently in preprint and it's under review. And basically, it's on this approach that they took, and they literally call it a deep learning recommendation model, DLRM. And it's kind of a mishmash of some of the approaches beforehand, and we'll see that it's kind of state of the art and has a really good accuracy and is really parallelizable. All right, so the first paper, Widen Deep Learning for Recommender Systems. Basically, the authors were trying to take advantage of some of the approaches to recommender systems and just like machine learning in general. So one thing they did was that they noticed that linear models were really good for recommender systems. So using things like logistic regression. And those were used because a lot of the features that existed for their metrics involved sparse features where there was a lot of kind of like binary indicators, things like whether someone installed an app or the device that they're using, or their gender, things like that. And these were really successful, but again, we were talking about using deep learning to kind of mitigate some of the engineering efforts that are involved. And also just the fact that deep learning models can get really, really high accuracies in terms of predictions. So they're kind of combining those two things. And that's where the name wide and deep comes from, where the wide part is coming from a linear model that's really quote unquote wide, where there are a ton of different sparse features that are being used for predictions, and then deep, obviously talking about deep neural networks. So we can see here from the image that they're combining these two different components, the wide and the deep. So first they have a deep neural network, which takes, first of all, the categorical features, turns them into embeddings, and then also uses those embeddings in conjunction with the continuous features, and just passes it through your typical deep neural network using ReLU as the activations. And then you also additionally have this wide part of the model where you're just taking the categorical features and doing just a simple like logistic regression on top of that. And these two different components are jointly trained, and that was kind of the approach that these authors took. So the way that they evaluated this recommendation system was they deployed it to different subsets of users, and they checked to see the difference in app acquisitions on the Google Play Store. And as you can see from the two tables on the bottom, using this wide and deep model as compared to wide linear regression, logistic regression, and a deep model, just like a deep neural network, there was actually an increase in the app acquisition of the users. And although kind of performance wasn't the exact focus of this paper, you can see on the right that they measured the latency in terms of giving recommendations to users. And it's from there you can see that it's kind of parallelizable, and the latency kind of subjectively is pretty good, 14 milliseconds. So the next paper that we're going to be going over is DeepFM, a factorization machine-based neural network for CTR prediction. And DeepFM was kind of like a direct improvement over the wide and deep network that we just went over. So basically what they did is they made it so that both components, both the wide and the deep components, use the same inputs. So what they do is they take all of the different input features, whether they be categorical or continuous, and they turn them into embeddings. And using those embeddings, they feed that into both the FM layer, which we will talk about later, and the hidden layer, the kind of deep part of it. And this pre-processing step is almost completely automatic, so there's not a lot of pre-processing that needs to happen as compared with the wide and deep model from before. So let's talk about the two different components that exist within the model. Although these images make it seem like they're separate, both of them are eventually being combined into the final output of the model. So first with the FM component, this is basically the same thing as the wide from before, where it's kind of capturing feature interactions between like the different features. So you can see there's this inner product going on between the different combinations of the dense embeddings, which eventually goes into the output. And over here on the right, you can see the deep component, which is a lot like your typical deep neural network, where it takes all of these different embeddings and passes it through X amount of hidden layers to finally get your output. So let's take a look at some of the results of this relatively simple change. You can see on the table on the left, there's this LR and DNN row, and that kind of corresponds to the wide and deep model. And you can see that DeepFM, in terms of the AUC and the log loss, they were actually able to achieve a better result with this model. And just to be clear, they were focusing on CTR prediction, which is click-through rate, just basically trying to predict and see whether or not users would click on a specific like ad or something like that, or a specific piece of content. And we can see on the graphs on the right that in terms of training time and pre-training time, that DeepFM, although it wasn't the best out of all the different models that they tested against, it actually had comparable results to those of the lower end. It had a pretty quick training time. So the third paper that we're going to go over is this deep and cross network for ad click predictions. So similar to the previous two models that we went over with the wide and deep network and the DeepFM, the deep and cross network uses two components, the cross network and the deep network, which they combine in order to get the final result. This model is also kind of similar to DeepFM, where the inputs are shared between these two different components. And where it differs is that the cross network, substituting for the wide component of DeepFM, specifically what they were trying to go for is the fact that wide and deep model and the DeepFM, both of them did not really take into account the fact that there could be higher order interactions in terms of the different like categorical variables. And so what the deep and cross network tries to do is it includes this cross network where they're able to add any number of layers to kind of account for different like higher order feature interactions. So if you look at the figure on the right, they have this cross network with layers x1 to xl, And basically, in the paper, they were able to prove that um, these different layers would eventually learn uh, a higher order feature interaction from the input features up to the nth order. So again, with this model, we see a relatively simple change, but as we'll see in the next slide, this relatively simple change actually led to a more effective model. So in terms of results, I guess the first place to start would be with table 1. You can see the deep cross network in comparison to a deep neural network or a factorization machine or a logistic regression, all kind of typical approaches to recommendation systems as we talked about before. The log loss of the deep cross network was much better than the rest. And it's kind of worth noting that the authors of this paper said that a 0.001 decrease in the log loss is actually a major improvement in terms of click-through rate. And these results are based on the same dataset as before, the Criteo dataset, which is based on a number of features of user behavior, and you're trying to predict whether or not they'll click on a certain ad. Some other results that you can see in terms of table 3 and table 2, you can see that in terms of efficiency, the deep cross network would need a lot less parameters in order to achieve the same log loss value as a deep neural network. And one of the other things that I wanted to mention is that in figure 3, we can kind of see how different numbers of layers inside the cross component of the network would lead to a general lowering of the log loss, basically kind of showing that using higher order interactions between the features can reduce the loss. And lastly, for this paper, I just wanted to note that DeepFM, the paper that we went over before this, actually the paper came out the same year, so they were not able to actually show any comparisons between this model and DeepFM. And now for the last paper that we're going to go over for this presentation, it's Deep Learning Recommendation Model for Personalization and Recommendation Systems. And so what this model does is it kind of takes some of the best ideas from the previous papers and creates kind of like a mishmash to create this state-of-the-art model that, as we'll see in the next slide, had really strong performance. One of the first things you'll notice is that the sparse features, the kind of categorical features, and the dense features are actually not being fed to each of the components of the model, which is kind of a departure from the previous 3 approaches that we saw. So what the authors of this paper did was that they created embeddings for both the dense and the sparse features, and they made it so that the size of the embeddings were similar between the two. This obviously created kind of a lot of overhead in the beginning in terms of pre-processing. So you can kind of think of it like a trade-off where these authors were trying to trade off some of the pre-processing, making that a little bit slower so that they could achieve a much more powerful state-of-the-art model in the end. So in terms of actual details on the architecture of this model, there aren't too many great visualizations or too in-depth details. Unfortunately, I think that's kind of one of the stipulations of having a preprint paper. But what the authors talk about and their approach, we can see from this figure on the right that they provided, where all of the sparse features are being input into 2 different neural networks. And right toward the end, we have this neural network that's kind of concatenating and combining all of the dense features as well as these 2 neural networks. And what that's doing in the end is ultimately it is learning the second order feature interactions between the dense features and the sparse features. And one of the things that they mentioned in this paper is that models like the deep cross network, while it might be more accurate to look at higher order feature interactions, in terms of performance and in terms of speed, it might be diminishing returns. So they're trying to explicitly just use second order interactions with this model. Here we can see some of the results of this deep learning recommendation model. They call it DLRM. And we can see they compare it directly with the Deep Cross Network, DCN, and over one epoch, the accuracy was overall higher than the DCN for both the validation and the training set. Once again, for the data that they're actually using, it's the Criteo digital ads data set. In terms of the efficiency, they actually have a breakdown of like how long each of the steps during training take. And one of the advantages that they specifically were going for with this architecture was that it's easy to parallelize both in terms of the model and in terms of the data itself. And you can kind of see that here with the breakdown of the training times, where a lot of the time being spent is actually just on embedding lookups, further proving that this model is kind of highly parallelizable and gives state-of-the-art performance. It's kind of a little bit unfortunate that they don't go into longer training times over like multiple epochs, but I guess that's unfortunately one of the drawbacks of having this preprint paper. Hopefully in the future they will have more results to look into, and personally I think that this model can end up with really good results in the future. Just based off what we have right now, it seems very, very promising. So with all these papers covered, I kind of just wanted to give a quick rundown and give some of the key observations that I saw while reading through the different papers. The first thing I noticed was that between all the papers, the authors seem to have like a very practical approach to coming up with these models, where they looked at previous work being done by recommendation systems, and they wanted to reduce the amount of time being spent on things like feature engineering, because in the end, right, these recommendation systems are meant to be productionized so that recommendations can be given to users. And it seems like the authors were kind of keeping their eyes on that, where they're trying to come up with models that don't require as much engineering effort up front, or even things like having the model be parallelized so that performance in production would be a lot faster. Another thing I noticed is that a lot of these papers would look at the work already had been done, and they would make small and incremental changes in terms of the architecture or the way that the data is processed. One of the last things I noticed was that all of these different papers seem to be taking different stabs at kind of the same problem, and there was kind of a lot of discourse in terms of how to incorporate feature interactions, which is kind of the crux of recommendation systems. And basically all these papers had a different approach and ideology behind how high order the feature interaction should go, how exactly should we model these feature interactions. And it seems like there's a lot of work and research to be done. Specifically, the last paper did talk about how this is a very high impact field of research, and yet academics are not really interested in it. And that kind of brings me to my conclusion, which is basically that this field is kind of relatively unexplored in terms of academics. I think neural network researchers and deep learning researchers aren't too interested in the practical applications with respect to recommendation systems. I mean, you can kind of even get a sense of that from the papers that I've gone over, where each of the papers was actually done by industry, not by, researchers from different universities or something like that. And personally, I think that's really exciting that there is such a high impact field of research that has a lot of work to be done. And I guess to anyone listening to this, I would encourage you to take a look and maybe give a stab at figuring out these recommendation systems and see what can be done and how it can be improved. With that said, that's pretty much the end of my presentation. Thank you so much for listening.